Hello, everybody. So we've been doing these type 1 projectile problems recently, and I think you guys are doing pretty good, but I know it's not completely easy. So I thought I might give a screencast, something you can take a look at if you need a little bit more help. So here's what the worksheet looks like. We did number 1 together in class. I believe we got you guys started pretty good on number 2 in class. Where are you? There you go. And so I thought I'd pay attention to number 3 here, if I can get this to move. This is one I want to come back to. Here's number 4. That's the guy we talked about, the ball outside the car. Maybe I need to talk more about that. Then this is one we talked about today because it's very similar to the lab that we did. We didn't have photo gates, but we definitely had something where we knew the velocity of the ball and then chose to find out, plotted to find out where it landed. We might do something fun with that tomorrow. And then the bottom was just more of that. So anyhow, let's go back to number 3. Can we skimmed over that and make sure you know about it? Okay, this is talking about old abandoned stone quarries filled with water. People like to mess around because they get filled with water over there. And so here's a guy standing on the top, and he throws a chunk of granite into the water below. He doesn't throw it straight down, he throws it horizontally with a velocity of 3 meters per second. It strikes the water 4.5 meters away. We're trying to find how high it is. So first thing we do is drawing. Here's a guy, one ball. Not very well, which explains why it only starts off with the velocity in the x direction of 3 meters per second, so 8 miles an hour. I think I can do better than that. We know this thing's going to go sploosh, and we know that happens 4.5 meters in that direction. And so this is 4.5 meters away. That's kind of a clue for that. We don't know too much else. It's horizontal, velocity of that. That's all. And what we're trying to find is delta y. How high is that cliff over the water? I'm assuming this is, why not? This is water down here. Okay, so you know what to do next. X, Y table. In the X, we know the distance is 4.5 meters. Do that. Okay, and then do we know anything? Oh, we know the velocity in the X direction is 3 meters per second. That's what we meant by throwing it horizontally. With the velocity of that, that says Vx horizontally. That's about all we know for that. Let's take a look at the y. Y, we're trying to find delta y. And it's falling because of gravity, and gravity accelerates everything at the same rate, so it's 10 meters per second squared. Now I could say it's negative 10 meters per second squared, and that's okay. It'll give you a negative delta y, which means it's falling down, and that works. That does the job. If you want to be a math purist, do it. But you can also decide that you want down to be positive, and then you'd have a negative displacement and a negative acceleration that would become positive if down were positive. So we'll live with that. All right, do I know anything else? I know the initial velocity is 0 because it's falling from rest from a purely horizontal start. And I think that's about it. But let's take a look over here. We've got our 2 big triangles that we love. We know velocity is delta x over t. We know acceleration is delta v over t. Those are 2 definitions. So if we build these triangles, I've got a delta x, I've got a vx. Hey, there's a delta x, there's a vx. I can find the time. Time is by itself, and delta x is over v, so it's delta x over v. So we can now say time equals delta x, which is 4.5 meters, over velocity, which is 3 meters per second. Meters cancel. And with a time of 1.5 seconds. And that is good to know, my friends, because the time that it is moving forward is the same as the time that it is moving down. So t equals 1.5 seconds for the down trip as well. Okay, so if we know that the time that is falling, and we know that the initial velocity is 0, that allows us to use our free fall equations, which are pretty handy. And they are, well, it starts with this. Sorry, I lost my pen for a second there. Get back to the red. And we know that means delta y is 1/2 a AT squared. That also means then that A equals the square root of, no, it doesn't equal the square root of anything. A equals, sorry, 2 delta y over t squared, and then t equals the square root of 2 delta y over a. So we have to ask ourselves, which of these three looks the most useful right now? We've got acceleration. We don't have delta y, so we can't use that one or that one. And we have time. Hey, we can use this guy. So we'll go delta y equals 1/2 the acceleration of gravity, so it's 10 meters per second squared, times the time squared. It's going to be times 1.5 seconds squared. I'm going to organize it a little better. Delta y equals 1/2 10 meters per second squared times, what's 1.5 times 1.5? 2.25 meters seconds squared. Multiply it all together and you get delta y equals 11.25 meters. So what that means is this is 11.25 meters high. I think that does the trick. So there's nothing remarkable about this problem. It's a really good example of how you can find many different things. We've traditionally been finding how far it will go in the x direction, what we've done in our labs, and a lot of other problems. You can also find how high things are as well. Okay, thank you. Hope you enjoyed that. See ya.